Welcome to This Explainer. Okay, today we're diving into a concept that kinda sounds like a magic trick. And honestly, it feels a bit like a riddle too. But it's actually an absolute, unbreakable mathematical guarantee. You know, human intuition is notoriously bad when it comes to probability. Our brains just aren't wired to easily grasp large-scale mathematical certainties. We're always relying on gut feelings, kind of just assuming the world runs entirely on random chance. But Today we're looking at a foundational rule of logic that actually dictates the hidden patterns in our world and totally cuts through all that randomness. We're going to start with this seemingly impossible proposition about human birthdays. It's this elegant piece of logic that I promise you, once you fully grasp it, you're literally going to start noticing it everywhere. So let's just get right into it.
Right, so I want you to picture this. You're walking into a massive, bustling banquet hall. It's super noisy, it's packed, and it's just filled with total strangers. Now you start counting the people in the room, and you arrive at exactly 367 people. Think about the sheer chaos of a crowd that size. You know absolutely nothing about their backgrounds, their ages, where they're from, or what their lives are even like. Without asking a single question to anyone in that room, and without checking a single ID, what is one absolute, undeniable fact you can state about that specific group? Like, what inevitably happens in a group of exactly 367 incredibly diverse people?
I really want to highlight the specific scale here. 367, not roughly 300 or about 400. It is a highly intentional number. Why? Well, it's exactly one more than the maximum number of days we can possibly experience in a single calendar year, even when we account for February 29th during a leap year. So I'm challenging you here. Think about what mathematical certainty binds these random strangers together just by them existing in the same room. If you lock them in this hall, what event is the universe actively, literally guaranteeing is going to happen?
Well, here's the absolute guarantee. At least two people in that room share the exact same birthday. And honestly, here's what's truly mind-blowing about this. We aren't talking about probability here. We're not saying, oh, it's highly likely, or there's a 99.9% chance. No, we're stating this as a hard fact, 100% certainty. You see, our brains usually assume that in a giant room, birthdays are just going to be wildly scattered across all 12 months. We instinctively think, surely everyone could have their own special day, right? But no matter how you try to arrange their birthdays, no matter how evenly you try to perfectly space them out across the calendar year, it is a mathematical inevitability that a collision is going to happen. Absolutely. At least two of those 367 individuals will be blowing out candles on the exact same day.
Part 1. The Pigeonhole Principle. Because look, this isn't some parlor trick or a lucky guess. It's an incredibly famous, absolutely unbreakable concept known as the Pigeonhole Principle. It's honestly one of the most delightfully simple, yet massively powerful tools in all of mathematics and computer science. It basically proves that within what looks like total chaos, certain overlaps are strictly unavoidable. The formal definition goes like this. If n items are placed into m containers and n is strictly greater than m, then at least one container absolutely must contain two or more items. Let's make this literal for a second just to see the intuitive beauty of it all. Imagine you have 3 pigeons, okay? But you only have 2 pigeon holes for them to nest in. You put the first pigeon in the first hole, then you put the second pigeon in the second hole. Now you have 1 pigeon left, but 0 empty holes. That third pigeon just has to share a space. It's a forced collision. It happens every single time.
Part 2. Items and containers.
To truly wrap our heads around the mechanics of the pigeonhole principle, we just need to take those abstract variables from earlier, the n and the m, and map them directly onto our real-world birthday scenario. We have to clearly identify what acts as our items to be sorted and what exactly acts as our containers. Notice the visual mapping here. Our n items, those are the 367 people. They're the moving pieces. Our m containers are the days of the year. And since we have to account for leap years to make this an ironclad guarantee, we use 366 possible birthdays as our maximum number of containers. Imagine literally handing each of those 367 people a numbered ticket, pointing them to an incredibly long wall of 366 physical boxes labeled from January 1st to December 31st, and asking them to stand inside the box that matches their birthday.
Now, the absolutely crucial point here is that condition. N is greater than m. 367 is greater than 366. Let's walk through this hypothetical scenario day by day just to see the tension build up. Picture person number 1 stepping up and taking January 1st. Then person number 2 takes January 2nd. Let's say this impossible streak of perfect distribution just continues all the way down the line. Nobody overlaps. They are perfectly filling up every single box. Finally, person 366 steps into the box for December 31st. Wow, this system worked perfectly, right? But wait, person 367 steps up. There are literally 0 empty days left on the entire calendar. So what happens? They are physically forced to share a birthday box with someone who's already standing there. The condition n is greater than m leaves the universe with no other choice. It completely forces the overlap.
Part 3. The generalized form.
So, as you might guess, mathematicians rarely ever stop at the simplest version of a rule. They immediately start asking, well, what if we have way more items? What if we have hundreds or thousands of people and only a few boxes? This naturally brings us to the generalized form. The generalized form tells us that there will be at least the ceiling of n divided by m items in one single container. Now please don't let those brackets around the n over m intimidate you. Those are just ceiling brackets. It's really just a fancy mathematical way of saying, do the division, and if there is any decimal or remainder at all, just push the number up to the next whole integer. So, for example, if your math gave you 1.1, the ceiling function just pushes it right up to 2, and simply a way to calculate the absolute minimum overlap you are guaranteed to find when your items vastly outnumber your containers.
Let's just break this down into 2 super simple steps so the math feels completely intuitive for us. Step 1, you just divide your total number of items, n, by your total number of containers, m. Then, step 2, you look at the result. If you get a fraction, that ceiling function just bumps it up to the nearest whole number. So let's say you had 733 people. Dividing 733 by 366 gives you roughly 2.002. The ceiling function takes that tiny fraction and pushes the whole thing straight up to 3. Meaning, with 733 people, you are mathematically guaranteed that at least 3 people share a birthday. Let's do one more rapid-fire example. What if you had an enormous group of 1,099 people? Divide 1,099 by 366, and you get just over 3. The ceiling of that is 4. So in a room of 1,099 people, you have a solid 100% guarantee that 4 people were born on the exact same day. Boom! It's just that simple. It is honestly fascinating how such a simple, logical rule about sorting items into containers scales up to reveal absolute certainties about the world around us. Which kind of brings us to a final thought for you to take away today. If the math is truly this unbreakable, what else is hiding in the pigeonhole principle? Like, did you know this exact principle proves that there are at least 2 people living in London right now who have the exact same number of hairs on their head? Because the population of London is vastly larger than the maximum number of hairs a human can physically grow, a collision is guaranteed. Or, hey, what about the fact that you only ever need to pull 3 socks from a drawer of 2 colors in the dark to absolutely guarantee a matching pair? Whether it's organizing massive computer networks or literally just blindly pulling socks from a drawer, this invisible logic is quietly organizing the chaos of our reality. So keep an eye out for those items and containers in your everyday life. Thank you so much for joining me for this explainer, and keep questioning the numbers around you.